let vector v sub 1 and v sub 2 be in the vector space V. And we want to show that H defined by the span of these two vectors is a subspace of V. So two important things to get us started here. We want to start by recalling that a linear combination refers to the sum of all scalar multiples of a set of vectors. We also want to recall that the span of a set of vectors denotes the set of all vectors that can be written as a linear combination of those vectors. So here we go. To get us started, we want to let vector v1 and vector v sub 2 be two elements in the vector space V. So we'll make a little love note here to ourselves that capital V is our vector space. And we should also make a note that H is, we could say H is equal to the span of the set of these two vectors, v sub 1, v sub 2. And we want to show that this is a subspace. So we want to show that H is a subspace of V. So we know that in order for H defined as the span of the set of vectors v sub 1 and v sub 2, that we need to show that our three properties hold true. So the first thing that we need to do is show that the zero vector is in the subspace H, or the potential subspace H. So to get us started, we let the zero vector be in our vector space V. And we're going to go ahead here and rewrite this zero vector as a linear combination of v sub 1 and v sub 2. So we can say that our zero vector can be redefined as 0 multiplied by vector v1 plus 0 multiplied by vector v sub 2. And this tells us that since H is the span, or the collection of all possible linear combinations, that the zero vector is in H. So we have met our first condition. And we now want to go ahead and show that this is also closed under addition. So we want to show that H is closed under addition. So just to recall what it is we're trying to show here, we want to show that for all vectors u and v in H, that the sum of these two vectors, vector u plus vector v, is also in H. So the first thing I want to do here is let vector u and vector v be two vectors in H such that they're defined as linear combinations of v sub 1 and v sub 2. So this will be such that vector u is defined as s sub 1 times vector v1 plus s sub 2 times vector v sub 2. And this is such that s sub 1 and s sub 2 are scalars. And we do the same thing for vector v. And let's choose another, we'll use c here. We have c sub 1 times vector v1 plus c sub 2 times vector v sub 2. And again, this is such that c sub 1 and c sub 2 are scalars. So these two vectors, u and v, are in H, defined by the span of vector v sub 1 and v sub 2. So now, let's take the sum. So we have vector u plus vector v is equal to, I have s sub 1 times vector v1 plus s sub 2 times vector v sub 2 plus c sub 1 times vector v1 plus c sub 2 times vector v sub 2. And we want to go ahead and regroup our like terms here. So looking at this, we see we have our vector v sub 1 terms that we can group together. So this will be s sub 1 times vector v sub 1 plus c sub 1 times vector v sub 1. And then we also have like terms here containing vector v sub 2. And we can group those two together. So I have s sub 2 times vector v sub 2 plus c sub 2 times vector v sub 2. And now we can go ahead and factor out our greatest common factor, which is the vector. So in our first case, we have vector v sub 1 multiplied by the sum of scalars s sub 1 plus c sub 1 plus, and then in case 2, our vector v sub 2 is our greatest common factor. So that's vector v sub 2 multiplied by s sub 2 plus c sub 2. And we have confirmed we have a linear combination here. So we'll make a note. So this is a linear combination of vector v sub 1 and vector v sub 2. And since the span is the collection of all possible linear combinations, it's going to be in H. So therefore, vector u plus vector v is in H, which is defined by the span of the set of vectors v1, v2. Telling us that this is closed under addition. So we have 2 of the 3 properties confirmed. We know the 0 vector lives there. We know that H is closed under addition. And last but not least, we now need to show that H is closed under scalar multiplication. And again, just to remind us, we know that this is for all vectors u in H and for all scalars c. We want to show that c times vector u is also in set H. So again, let's let vector u be some vector in H such that we'll use the same linear combination as before. So I have s sub 1 times vector v1 plus s sub 2 times vector v sub 2 such that s sub 1 and s sub 2 are our scalars. And we also want to let c be any scalar. Again, here we're restricting ourselves to the reals. So let's go now and take the product. So I have scalar c times vector u. So this is c multiplied by the linear combination s sub 1 times vector v1 plus s sub 2 times vector v sub 2. And by the distributive property here, we know that we can rewrite this as c times scalar s sub 1 times vector v1 plus c times scalar s sub 2 times vector v sub 2. And then grouping together our scalars here, we can say that that's one scalar defined by the product c times s sub 1 times vector v1 plus one scalar defined as c, or defined by the product c times scalar s sub 2 times vector v sub 2, which is a linear combination of v1 and v2, which is what we wanted to show. So we have redefined this as a linear combination of vector v1 and vector v sub 2, which by definition means that therefore c times vector u is in H, which is defined as the span of vector v sub 1 and vector v sub 2, which tells us that H is closed under scalar multiplication. Woohoo! And so we have confirmed our third property here. And we can make our beautiful final conclusion. Therefore, since all three properties are met, or since all three properties hold true, we know that H defined by the span of vector v sub 1 and vector v sub 2 is a subspace of vector space V. And this is a super duper important concept here that we've shown in 2 dimensions. And we're now going to take this and extend this into Rn with our next theorem.